Okay, so anyway, what we're doing here is kind of laying the foundation, and this word here, this thing called equilibrium, is, oh, I know what it was. I think the one thing in insect collection did help is that it made you more of an observer. Because if you knew you were looking for certain kinds of insects, when you're walking on the sidewalk during the insect collection, didn't you say, do I have that? Do I have that? Did it ever happen to you? So, and it made you, I like the fact that it made you go to places like maybe you had to go to a pond, maybe you had to pull over a rock, and it made you go observe more. And so what I'm saying here is, what I'd like you to be able to do now with this equilibrium thing, it says, if I ever see an object that's sitting still, like I look around the room here, any object here that's sitting still is at equilibrium. Now there are forces acting on the object, right? That table, that the earth is pulling down that table, but it's not going anywhere. There must be another force, isn't there? And so the floor is pushing back on the table, isn't it? If I can get you to think like that, it'll open up your eyes. Another thing is, what if somebody pushes a box along the floor and it's going at a constant speed? What if that box is going at a constant speed and you're pushing against the floor? You're pushing along the floor. What can you say about that? It's also in equilibrium. How can that be? I see the person putting a force on the box. They're pushing the box. How can it be a net force of 0? What do you think? Everybody should be able to answer this one. Yes? There has to be. There has to be. And matter of fact, we call it friction. And one of the frictional forces would definitely be pushing back here, right? And which one's greater, this push or that push? They have to be equal. Now, one thing that's really weird, and I'll have to teach this to you. You might say, wait, if the forces are equal, then why would the box keep moving? See, that's a great question. Anybody have an answer for that? A jet, 1,000 miles an hour, 1,000 miles an hour, 1,000 miles an hour. What's the net force on the jet?
0. Zero. I thought you were talking about the force coming back.
Okay, now, all right. So, wait. So let's say the net force is 0. The next question is, then why does he keep moving?
Because it's constant.
Be careful.
That's how it works.
Yes.
Is an object in motion?
Yes, the inertia.
Good job, Walker.
That's the law of inertia. That's Newton's first law of motion, law of inertia. An object at rest has a tendency to stay at rest. An object in motion has a tendency to stay in motion in a straight line at a constant speed unless acted on by unbalanced forces, okay? Now, that's going to be hard for you to think. What inertia? That was some word in middle school that I had to have a matching on, and I just had to know the definition. Are you talking about something real? Is that real? Objects have inertia? And here's some weird things about physics. What is inertia? The tendency of an object? What the heck? What color is a tendency? Hey, what's a push or a pull? I mean, what's a force? A push or a pull? That's not so scientific. Well, we have ways to describe things, but we don't know that much. We know about it, but we don't know exactly what they are. What is a push? Yes?
Does the weight of an object, does the weight of an object affect its down, or the Earth's pull on it, and that's why something's very
Okay.
harder to lift?
All right, now, the weight of an object is the pull of the Earth on the object. Weight is a force. Weight, the pull of gravity is a force. It's called weight. Now, you might have asked the question, does weight affect the amount of friction? Yes. So imagine the box, and if you could see it microscopically, it'd be like a mountain range upside down. If you could really, it feels smooth in my hand, but it's not really that smooth. See that? And then here's a tabletop, another set of mountain ranges. Ready? And I'm going to push the box. Boom, 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 boom. See that? And that's the theory about where friction is. Now, are there engineers? I've seen it, where they try to make a near frictionless table. And they try to fill in all the holes. There's almost no microscopic bumps. And you put one piece of steel in another, and it slides right over the other one. Yes, that costs a lot of money to make that. Yes?
Isn't it done the same, like the frictionless is achieved? I think they're called hydrostatic hydrostatic bearings, but basically they pump a high pressure oil in between the surfaces, since it's not compressible,
So we could do that if we could put something between those two pieces of metal so they wouldn't be in real contact. And that's what we do, oils. That's why we use any kind of lubrication, oils. We
It's
try
like
to,
those fountains where they have that big round ball that just rolls.
Yeah.
It's not on bearings, it's just there's just a hole with water coming out of it.
Yes.
okay, so,
That's all that's supporting it.
so once it starts spinning, it's gonna have a tendency to keep spinning, as long as there's not too many frictional forces to slow it down.
Yeah, and then it's in a bowl.
And does it kind of keep going though?
Yeah, with the water's coming out next to it, but it weighs a couple 100 pounds. But you could just spin it easily with your hand, but it's just floating there.
You would have to overcome the inertia of the ball. But once you overcame the static inertia, once you overcome the inertia and got it moving, it then have a tendency to keep moving like that. All right, when you see things in space or you watch movies nowadays, they all have consultants that are scientists, and they say, people are pretty sharp now. We need to make a movie where that's really what would have happened,
Especially
and so if you watch things on movies, if something starts moving and there's no force to slow it down, it'll just keep going at a constant speed, and forever and ever, it'll just keep going. The good news, a lot of things in space, when they're moving, they have gravity. They're in a gravitational field. So most of them, even if they're going around the Earth, they might be getting a little closer, and then it goes in the atmosphere and they burn up. That's the good news for a lot of things like that. Okay, but if you were in orbit around the moon, think about that. I might get closer and closer to the moon, but I just kind of run into the moon. And if it's something big, it would run into something, wouldn't it? It wouldn't burn up. There was no atmosphere on the moon. Okay, so are you okay on this page here about vectors? Okay, now, I think the last page we read was this guy here. And I know that I made you listen to that page where Paul Hewitt was kind of telling what happened to him. He was being told, don't go into math, don't go into science. That's not your strong point. And what he ends up making lots and lots of money writing science books. He went back to school. And this guy named Burrell, he was just a question asking, wasn't he? That's really a lot of science is, can ask questions and try to answer them. And so it really motivated him to say, I don't know. I don't know this. Why don't I know this? And he went back and said, I'm going to make a physics book that's a little different than just the math, plug and chug math books, okay? And there's nothing wrong. If you want to be a real physicist, you're going to have to do the plug and chug math. You're going to have to use calculus. I understand that. But what about people who might be interested in physics, but maybe they don't like math? They can still like physics, even though they might not go to college and become a physics major like that. Okay, what do you call if that book right now is on the table and the Earth's pulling it down, but the table's pushing back up? What do you call that push back with a force that from a horizontal surface, or maybe not horizontal, that pushes back? What's that called? The support force. What's the other name? What's the other name? Normal force. Everybody get that? If you talk to a physics person, they'll say, well, they use that one because their professors use that word, because their professors had used that word. And support force or normal force, they call it, all right? Okay, this is where we left off. And did we read this page about remember doing this or not? I'm going to have you, we're going to do more than just read today. We're going to have you actually do something. So did we read this page at all? Okay, and what it says here is if you were talking about an object that was sitting still, that would be called static equilibrium. And in this one, what is this one called? What is it? Okay, and it says here, there's another way to be to equilibrium. You could be moving in a straight line at a constant speed, and that'd be dynamic equilibrium. Dynamic means moving, like that. Okay, but we already talked about that idea, so we're going to go on. Now, let's go over here, and this is gonna make sense to you, and then I'll give you a worksheet to work on, but, so here, this is a spring scale that measures forces, and if we hook it up here to a rope, it'll measure the tension forces. Everybody got that? The tension. And so the earth is pulling this person down. Also, when you write your own book, you get to, he was an artist. He drew all these pictures, everything in the book as his artwork, and every picture in this book is a relative or a friend of his. When you get to the point where you have written your own book, and this is like the 8th or 9th edition, whatever it is, and you made a lot of money for the book company, and you say, the next one, yeah, but all my friends, every picture in here, if you see a person in here, that's somebody he knows. One of them is his wife, one of them is his friend, one of them is Burl. Anyway, he also drew all the drawings, and he also gets to name them. And what do they name this person? Nellie. Okay. Anyway, this is Nellie. And Nellie is hanging, and Nellie weighs 300 newtons. And Nellie weighs 300 newtons, but she's sitting there. So what is the tension in this rope? 300 newtons up, isn't it? And remember, in the vector world, we have magnitude and direction, don't we? So 300 down, 300 up. Okay, now, if Nellie hangs from 2 ropes, each spring scale will read how much? 150 up, 150 up. Okay, that was pretty easy. I'm going to remind you about the conversion factor. And if you'll take a look right here, on the Earth, if you're near the Earth's surface, I mean, it's not on Mount Everest, you're not on the moon, but if you're near the Earth's surface, and we all are, 1 kilogram of mass, this is mass, equals how much weight? And weight is a force, isn't it? So a kilogram of mass equals how much weight? 9.8 newtons. Now, we're going to use 10 for conceptual purposes, get that? But if I ever ask you to do an experiment, I would want you to use 9.8. Get that? So it's really 9.8 newtons per kilogram, but we're going to use 10 so we can kind of think about it like that. All right, so if I want to convert Nellie's 300 newtons into kilograms, I could do that. That would tell me how many kilograms she is. And then what is the conversion factor to make it seem like you're in the United States? A kilogram is 2.2 pounds. Does everybody know that? 1 kilogram is 2.2 pounds. So if I held a kilogram, you say, oh, that's a little over 2 pounds. You're right. How about 2 kilograms? That's a little bit less than 5 pounds. That's right. You got it. So anyway, there's conversion factor there. 1 kilogram of mass on the Earth is about 2.2 pounds. So I don't know why Nellie only weighs 66 pounds. That's not very much, but maybe it's a small girl. Okay. Okay, let's go on. Now, what I want to do here, you can see that I've written on the book many years. And so what I'm going to do is I will try to show you what I wrote here, and then I can do it on another piece of paper. So what I want to do is they're going to talk about how do you add vectors, and we're going to try that a little bit today. So what I'd like you to do is I want you to maybe Kinsley can help me. Kinsley, go all the way back there and get that whole rack of rulers out. Left, go left, left, left. No, the other left. That's it. There you go. Now, okay, there you go. There you go. Now, what you're going to do is point to one other person, and you can give half the class a ruler, and the other person give the other half a ruler, okay? So let's everybody get a ruler and a piece of paper. Okay, get a piece of paper out, and so what we're going to do is I'm going to show you how to add vectors. All right, here we go. Now, I need to show you, number one, the classic way that every physics person thinks when they're adding vectors, and it's the way the book emphasizes this. But then I also will show you a second method, which I like myself, and you can use either method. But I will tell you that since almost all the diagrams in the book use the parallelogram method, you have to make sure that you know how to do the parallelogram method. You got that? So what we're going to do is we're going to take two vectors, and I'm just going to, by the way, when we do vectors with a ruler, we do scale drawings. Like a vector that's 5 newtons long would have to be longer than one that was 2 newtons long, right? And so why don't we just use 1 centimeter equals 1 newton? You want to do that? That's my scale. So why don't we draw a, I don't know, how about a 4 newton line, 1, 2, 3, 4. Why don't we write, let's do a vector that says 4 newtons. Now, I drew that 4 centimeters long because 1 centimeter is 1 newton, and that's my scale drawing. And what I want to do is, I'd like to add to it, now everybody knows, let me draw another one. I'm going to draw a 3 newton straight up vertical. There we go. 1, 2, 3. Here we go. Okay, now, the question is, how do you add those two vectors together? How do you add those two vectors together? Well, we know that if they had been going in the same direction, what would the answer be? What was 4 newtons this way and 3 newtons this way? 7 newtons that way. What if they were going in opposite directions? 4 newtons this way and 3 this way, what would the answer be? 1 that way. Those are the easy ones. But we know that the answer could be anywhere between 1 and 7. The answer could be 5.555. It could be any of those answers. And so the next one is, this is the way that the author is going to show you how to do it. They're going to say, and by the way, we need to have a little vocabulary here. This is called a vector. And it's a scale vector. And this is called the head of the vector. And this is called the tail. That's pretty easy, isn't it? Okay, now, so the author is going to show you how do we add two vectors. He would say, draw the vectors to scale with their tails together. So let's go ahead and do that. We're going to put their tails together. All right, so I'm going to do that. I'm going to redraw it. And so here's my 1, 2, 3, 4. Here's my 4 Newton vector that's going to the right. And I'm going to attach the tails together. So I'm going to do a 3 Newton here, and there we go. All right, so is everybody okay on this? Now, it just so happens that these happen to be at 90-degree angles to each other, and when they're not at 90, I'll show you that too. But for right now, we'll do the simplest ones we can do. Now, what they're going to ask you to do in the parallelogram method is to redraw this one over here and redraw this one over here. Okay, so let's do that. So the first step you do is you put their tails together, and then you redraw to form a parallelogram. And I think your math teacher probably uses something like, is that what they use for a symbol for parallelogram or something like that? They use a symbol? Okay, so what I'm going to do is, let's go over here, and we'll recreate this one, and so I took this one and I recreated over here, didn't I? And then I take this one and I recreate over here. Now this happens to be a special parallelogram because it's a what? What else is it called? This is a special kind of parallelogram called a what? Rectangle. and I'll show you when the angles are not 90-degree angles, we still can make a parallelogram out of any two vectors. You get that? Okay, now, so now what's the author do to say next is it'll say draw the diagonal. Draw the diagonal, and this is my starting point here. See that? This is where everything started, where I put the two tails together. And now what I'm going to do is draw the diagonal. I like to draw the diagonal dotted line. I should not have drawn this one dotted line, sorry. I'm going to fill that in. Okay, now, and then where's the head of the arrow at, though? Where is the head of the vector? Down here or up here?
Up there.
See, the tails, all the tails are together, aren't they? So here we go. There's my answer right there. The diagonal is called, there's a special name. What do you call the answer to a vector addition problem? It's called the resultant vector, okay? So the resultant is the answer. So what is the answer? The answer is a vector like that. So if something happened, let's say you were playing pool and you had a ball here, and some ball hit your ball with a 4 Newton force this way, and at the same time, another ball hit it with a 3 Newton force that way. Would the ball go, ooh, 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 like, I got hit, or would it act like a single vector hit it? It would. And how big would that vector be, and what direction would it be in? That ball will not go off in that direction. The ball will not go off in this direction. What will happen? The ball will go off in that direction as if it was hit with this vector here. Now, the good news about 90-degree angles is that you guys all know about triangles, don't you? As a matter of fact, I picked the world's most famous triangle, one of them, called the 3-4-5 right triangle. And everybody know about the 3-4-5 right triangle? Any combination of that, here, double all the numbers. You mean like the 6, 8, I'm sorry, 3, 4, 6, 8, 10? That's one. How about the 300, 400, 500? Yeah, that's a right triangle, isn't it? Any ratio that's 3, 4, 5, you know it's a right triangle. So let's go ahead and do that. So I know that this is a right triangle, and I want to find that out. And you say, well, that's the hypotenuse, isn't it? And so you could do this. The resultant vector, that's this guy here, would equal what? Wouldn't it equal one of the legs squared? Isn't that right? Plus what? And so the resultant would be, I'm sorry, my fault. Didn't the Pythagorean theorem say this squared plus that squared equals what? That's squared. Okay. So if you want to find the magnitude, what would we get? So what is the resultant going to be? And what do you think? 5, isn't it? So what's going to happen is the pool ball will act as if a 5 Newton force hit it from this angle, and it will take off like that. Ever get that? Again, this is pretty simple because I'm keeping it at 90-degree angles, but at least you understand sort of how we did that. The one thing that bothered me about the vector world is I like math class. I like that. And a lot of stuff I did in math were the mechanics. Oh, you can give me 10 of these problems. You know what? I'll get them all right because I know this squared plus this squared equals that squared. You give me another one. This squared plus this. That's called mechanics. It doesn't mean you're thinking about it. It just means that you can do it. You see that? There's a lot of stuff we do in math, even in science, you gotta be careful. There's a lot of things you do in science but you don't know why. I remember the one time they said, hey, you got a piece of steel whose density is 8 grams per cubic centimeters. Let's cut it in half. What's the density of that? I got tricked once, and then I knew, say 8. I cut it in half again. It's still 8. But I didn't know why. I just knew that the density of half that bar of steel, I would have thought was 4, but it's not. No one took the time and talked about ratios. You get that? If you have a ratio and both the numbers get cut in half, what happens to the ratio? What if you cut them in half again? What happens to any ratio? Take any number. 100 divided by 50. What do you get? What's 100 divided by 50? 2. Cut them both in half. 50 divided by 25. 2. 25 divided by 12 and a half. 2. You see that? Yes, no? I couldn't tell you back then why half of the bar of steel had the same density, because I just knew how to do the mechanics of it. See that? So what I'm asking here, here's something that's going to bother you a little bit. If you love Pythagorean theorem, you said, are you kidding me? That's nothing to me. I can do that in my sleep. Let me tell you what you're not going to like. What is this vector plus this vector? What does it equal? It equals that vector. You're not going to like that because, no, in math class, this squared plus this squared equals this squared. I can use that to find my magnitude, but here's what's happening in the vector world. What does that vector plus that vector equal?
A vector.
That one. It's true. What is this vector plus that vector? It equals that one, period. I use Pythagorean theorem to figure out the magnitude of that vector, but in essence, this vector plus that vector, what's this plus that? This. That is the resultant vector. Okay, so we have to think a little bit differently, okay? Now this is called the parallelogram method, and what I want to show you is, I'll show you in a book how the author would have done this. And I'll tell you the biggest mistake that people make. I'll tell you the big mistake that people make, because right now some of you are thinking, this is so simple. It will get more difficult, but be careful about thinking it's simple. So, for example, look at this. See this? When you put the two tails together like this, every year I have somebody, they do this with a ruler. Oh, it's a triangle! It's a triangle! And you think that's the resultant vector. That's wrong. That's completely wrong. There's no way that this plus that equals that. It doesn't. It equals this one. Now, how do we get that one? You had to redraw that one and redraw that one, and then the diagonal became the resultant vector. Every year I have people, when they draw these two together, they think, well, I better close it up, make a triangle. No, don't do that. Okay, questions on that? All right, so now let's try this. What if I had, oh God, what's my camera here? Whoa. Bad time to go off. There you go. Okay, what is this vector plus this vector? And just look in the book. How would I find that out? I redraw this vector over here, redraw this vector over here. You see what they did? See how they redrew this one over here, they redrew that one over there, and what's the answer going to be? The diagonal. Does it make sense to you that if something were to push you this way and that way, what would happen? You would go that way. When they made, a long time ago, I don't know how much history, do you ever talk about the Erie Canal? This was big. Back then, if you could take things from the Michigan, Indiana, Ohio area, and you could move them all the way to maybe New York and stuff like that, wow, you could have a booming business, right? And so they had places in the country where they would dig out canals, and they had water in them. Because if you had a great big boat and had a lot of stuff in there, you really didn't want to go over the land, you had to have horses and stuff like that. If they were on the water, there was less friction, wasn't there? And it's a lot easier to move a boat full of material on the water. And so what they did is, they had the Erie Canal, and then they had little paths on both sides of the canal, and they had a horse here, and maybe a horse here, and a rope. And so what they would have done is something like this. They would have said, here's the canal, and here's my boat. Hey, I gotta get that boat down there. It's got a little good stuff in there. I'm gonna make some money. And you say, so what you did is you would tie, you could tie this to one animal and tie this to another animal. And I'm pulling, which way am I pulling? I'm actually pulling this way. I'm making a vector like that, aren't I? And what are you doing? I'm pulling this way. Which way the boat's gonna go? straight. Oh. So as long as you kept these animals pulling at about the same force, then that boat would go right straight down the canal like that. So there's so many applications of vectors and vector additions that let's take a look at this next one here. Now here is Nellie, and Nellie likes to hang around. I guess that's her job, hang around things. But let's say that Nellie weighs 300 newtons again, and the question is, how much will this be? How much tension will be in this rope? Now, if you remember Nellie before, when one rope held her, what was the tension in the rope? I need you to pay attention, okay? If Nellie weighs 300 and she's standing there, all right?
300 newtons.
There would be 300 newtons of tension in the rope, right? What if she would hang on with 2? 150? 150. Oh, only half her weight. Okay, that sounds pretty good. So now let's do 2, and they're not straight up and down. Now what happens? What happens when you do that? What's the tension? Is it going to be, do you think it's going to be 300? Well, no, there's 2 ropes. Do you think it's going to be 150?
Yes.
And let's find out. So what happens here is there's a tension. Now, here's the hardest thing about drawing these little diagrams. The length of the rope doesn't matter. It's the tension in the rope. When I draw this arrow, am I drawing the length of the rope or the tension in the rope?
Tension.
Okay, so that vector that I'm drawing is the tension in the rope. So what I'm going to do is, see this little arrow here? What does this represent? It starts with a W.
Downward.
Weight. This is her weight, okay? Now, Nellie's not going anywhere, so somehow, there must be an upward force of 300 newtons. Somehow. How do I know that? The Earth's pulling down 300, and Nellie's not going anywhere. There has to be an upward force of 300. Isn't that right or not?
Yeah.
Where'd that come from? 1 rope? No. 2 ropes straight up and down, 150, 150? No. But some combination of this plus what?
That.
This plus that has to equal what? 300. Now here's the hard thing about drawing these, okay? So let's take another page here. Let's pretend that this is Nellie, and what I'd like you to do is, if you can, there you go. Try to draw the angles about the same. So let's say, okay, here we go. Now let's draw a weight vector. Okay, now you decide how long you want to draw that, okay? If you want to draw it 3 centimeters long for 300 newtons, you could do that. So let's say that's 300 newtons. And now, what I want to do is I want to draw another vector straight up, the same size. Does that make sense to you? Okay, now I'm a little off on my drawing. There you go. Okay, are you okay on that? But instead of 1 rope helping Nellie, I want to draw ropes at angles. Now, I want you to be kind of careful with the angles. Try to make them the same. Can everybody kind of do that? So make this angle the same as this angle. Can you do that? All right. Okay, now, are you okay with this? Now, somehow, we know that there's going to be a tension going that way and a tension going that way, and when you add them together, it's going to be 300 up. So here's the hard part. When I'm getting ready to draw my drawing, the parallelogram method, take my ruler right here. Let me go ahead and draw that nicer line here. Now, look at my ruler. I've got to draw this one again. So what I'm going to do is, whoops, I got to watch my carrot. Okay, watch now. Move it until, when do I stop moving it? Boink, when I get to the top of that arrow. Are you okay on that? Okay, now I turn my ruler like this, and I move it, stay there, stay parallel. When I get to the top of that arrow, I stop. Okay, now, so guess what? Remember, the rope is not the vector. The arrow, the tension on the rope is a vector. Got that? So these are the two vectors I want to know. How much, what is this tension going to be in this rope versus this rope? You okay with that? Now, this vector has been redrawn over here. This vector has been redrawn over here, and the resultant vector is this one, isn't it? All right, can everybody see that? Okay, now, one way we can do this without using mathematics, if you did a scale drawing, let's say you made this 3 centimeters long. Therefore, 1 centimeter equals 100 newtons. All right, so let's say I did a scale drawing. What's a non-mathematical way of finding out the tension in this arrow? You could measure the length of it. Now, let's say the length of this is 2.5. So what would the tension be in that rope? How much? Yes. Now, again, I didn't, if you drew yours to a scale drawing, did anybody else actually measure theirs? What did yours come out to be? It was actually, so I don't know what angle you picked. Can everybody do that? So without using any mathematics at all, I could say that the tension here is about 250 newtons. That's a lot, isn't it? So, and have you ever seen a gymnast hanging like this is much easier than doing what?
Hanging like that.
Hanging like that. Why is this so much harder? And it's a vector thing, isn't it? That force plus that force has to equal that, isn't it? So if this was one strand, if this was my whole weight, let's say 200 pounds, ready? 200 pounds. Okay, I can feel it. 100 pounds in each arm. Okay, that's nicer. I like that one. Ooh, what happens now? It was 200, 100 each rope. Now what? More than 100 each rope. A lot more. Have you ever seen people, a gymnast, do that? Oh. Think about the vector world there. That's not exactly straight. They make it look pretty straight, but think about that. That vector there plus that vector there, they had to equal my weight. Unbelievable amount of force. Okay, so you ever see how to do this now? This is how you do it without using mathematics. I'll do mathematics, maybe I'll do it tomorrow if we're here. Now, I would like to show you, and I will tell you that almost every physics book I've seen, they use the parallelogram method, and if you've actually drawn this once, you'll understand how to do it. I do want to show you another method that the book does not show that I think is kind of interesting, all right? And so method number 2 is called the tail to head method. And I'll tell you why I like it. What I'm going to do is just pick a vector and let's do the same one we did before, right? I'm going to do 1, 2, 3, 4. I'm going to pick that one. 4 newtons this way. And I'm going to add it to a vector that is 3 newtons up. Oh, dang it. Okay, all right, so anyway, so what if I had to add these? Another method is to pick either one of the vectors. Pick either one and lay it down first. I think I'll pick this one. I'll pick this one first. I didn't have to, didn't matter. And now what I'm going to do is put the tail of the second vector onto the head of the first vector. Okay, so I'll put the tail of the second vector onto the head of the first one. Everybody see that? And now the resultant will be from the first tail to the last head. From the first tail, and this is my resultant, and look what happens there. Now you might say, well, why do you want to teach me this when the physics books want you to do the parallelogram method? I want to show you something that I think is an advantage of the tail to head method. First of all, guess what? I didn't have to redraw those other two lines, did I? And I very clearly see where the resultant is, don't I? Isn't that the resultant vector going that way?
Yeah.
I get the same answer. And I can add these in any order. If I would have laid this one down first and then laid the other one down, I still would have gotten the same answer. And here's what I like about the tail to head method. What about this? Uh-oh. What's 2 newtons plus 3 newtons plus 5 newtons? And I'll tell you what I like about it. You pick any one you want. Pick any one you want. Which one do you like? And I won't use a ruler right now because I'm in a little hurry, time crunch. Which one do you want to pick first? It didn't matter. You want to do that? 5? Okay, let's do that. I hereby declare that I'm going to draw that one first. There's my 5 newtons. Now, pick another one. It doesn't matter which one. Which one? 2? 2 up? Okay. And then what's the third one? That one? What's my answer? Right here. There's my answer right there. Now, if I did a scale drawing, I could actually measure that and actually tell you the magnitude of that vector, couldn't I? Now, a lot of you don't believe me when I said it doesn't matter which order. Let's pick another order. What do you want to start with this time? Pick one. Pick one, Jessica. The 3? Let's start with the 3. What do you want to add to it? Doesn't matter. The 5? Okay. I'm running out of space here. And then what do you want to add to it? The 2? All right, what's the answer? Oops, sorry. I should have done a scale drawing. And I get the same one. I still get the same answer. What I like about it is you can add more than 2 vectors at a time if you wanted to, and you can add them in any order. That's what's neat about the vector world. You can add them in any order, you'll still get the same resultant. So I would say in most cases in a physics book, they're usually talking about 2 forces at a time. That's why I think they use a parallelogram all the time. But if you ever had a situation where you add 3 vectors, 4 vectors, 5 vectors, I can see this one as being also a little bit faster. This is a scale drawing, isn't it? All right, so right now I think that's enough for you. I didn't want to use any trigonometry today. I know some of you are thinking, is there another way to do this? And there is, but we're not doing that today, okay? Now, what I'd like you to do is at home, I have, here's what I'd like you to be working on. And probably by Monday, see if you can have this done by Monday. We'll see what happens if we have school tomorrow, but if not, maybe it'll be on Tuesday. But at the end of the chapter, I would like you to do questions 1 through 24, and then here are the next ones, 26, 28, 29, 35, and 39. Now, I'll put this on Google Classroom in case you want to, if you didn't write it down today. But let me tell you that I think you'll find these questions to be not too bad. Here's question number 1. What is the difference between force and net force? I'll tell you a real quick story. When I was in Indiana, I've been here a long time. I've been here since 1983, so you weren't even born. But I've been in North Carolina for a long time. But I was in Indiana before I came here. And we had, I coached high school volleyball, and I actually had some other people, some adults that wanted to be in an adult league, and so I kind of helped them. They didn't know very much about volleyball, so I just wanted to help them, and so I was kind of like the captain. But we had a friend of mine, who worked at a gas station, and they said they'd be willing to put money up for shirts, because it was kind of neat. Here I am, 28 years old, whatever. And so we had these adults playing in an adult volleyball league, and we got to make shirts. And back then, it was a little bit harder to make shirts than it is now, but but we had a volleyball team, and it had the logo of the company, and we had to come up with a name. And so, guess what the name of our volleyball team was? That's right. What was it? Net Force. Anyway, I thought that was pretty. Okay. All right. Thank you very much. Thank you very much.